The framework for analysis of schedulability, timing, and resources is a plug-in to the open-source AADL tool environment. The tools perform computer system resource loading and timing analysis and ARINC 653 schedule generation and visualization. In this video, we'll do a quick walkthrough of a few example models and scenarios that come with the tools. But first, we'll mention some system architecture modeling practices that the tools support. First is the concept of progressive modeling. Models start out simple and are then elaborated with increasing amounts of information as development progresses. This reduces modeling effort by building on earlier work. This also avoids creating multiple models that may later become inconsistent with each other. Traceability and compliance of later detailed models back to initial requirements models is supported using the dependency and legality rules of the modeling language. Different parts of a model may be filled in to different levels of detail. As we'll show in a few minutes, the tools adapt to different amounts of detail in different parts of a model, what's commonly called mixed fidelity modeling. The amount of information in the analysis reports increases as the amount of detail in the model increases. Architectures and their models are layered. For example, software is often developed to execute on a virtualized execution platform that is later detailed in different ways for different systems. In AADL, binding declarations are used to allocate software demands to virtual and physical resources. Systems are heterogeneous. Different subsystems are scheduled in different ways. Some subsystems may be synchronized, but different subsystems may operate asynchronously with respect to each other. These concepts and more are discussed in the Architecture-Centric Virtual Integration Process Modeling and Analysis Handbook, which is available on the CAMA website. FASTAR, as the name implies, is a framework that integrates a variety of specialized tools so that heterogeneous systems can be scheduled and analyzed at varying levels of detail. We'll quickly step through utilization analysis, schedule generation for ARINC 653 modules, and finally schedulability analysis of mixed fidelity and layered heterogeneous networked system models. The Defense Acquisition Guidelines say that preliminary software and resource loading should be covered in the SRR. The Utilization Analysis tool supports this. Utilization analysis is typically done at an early phase. Models may show little more than a preliminary breakdown into software and hardware configuration items with rough estimates of demands and supplies. This first diagram from the FASTAR Get Started example that comes with the tools is about the simplest model that could be written and still get some utilization analysis results. The model has two AADL systems in it, one named Applications that has some demands and one named Platform that can supply resources of different types. The dotted lines in the diagram represent binding declarations, and that's the way that demands are placed on supplies for different kinds of resources. In this one, there are memory demands, and there are also bits per second demands and MIPS demands. Those are the standard resource units supported by the AADL standard. The utilization tool also allows users to declare their own types of resources. For example, users might define GPU operations per second or FPGA configurable logic blocks if those are important resource units in a particular system. An example project that shows user-declared units is included with the tools. In this model, you select the system instance you want and instantiate, and that causes an instance file to be created for the system model you want analyzed, and then you click the little green check mark. That will do a utilization analysis of this model. An analysis folder will appear and an HTML report will appear. Now, in each report, there is a section for each system operating mode Within that operating mode, there is a section for each resource, and for each resource, there's a list of analysis results. The first row is the combined result. This is the total demand that's placed on that resource. This is the total supply that's provided by that resource. This is the utilization on that resource. A limit that has been placed by the user. This shows 1, but the user can set a lower limit for management reserved. And a figure called the margin. This is the sensitivity analysis value. And what this means is that the total supply demands on this resource could be increased by a factor of 10, and you would still be feasible. There is also one row for each individual demand that's placed on the resource. In this case, there's one row because there's one application. The MIPS supply in this row is apportioned among all the demands placed on that resource according to those demands. In this case, it's not split apart because this is the only thing that's placing a demand on the resource. And it lists MIPS demands and so forth. Now, we can go to a more complicated version of this where we have added some additional details in the model. We've taken the original application and expanded it into 2 processes. We've taken the original platform and expanded it into 2 processors and a network. If we instantiate this one, and we then perform a schedulability analysis on this one, then it produces a new analysis report. Now in this case, the original layer, the original resource, virtual resource now, the platform is still shown, but additional sections appear in the report. There's one for the platform network, and one for the platform processor A and platform processor B. And in the case of the demand placed on by the application on the platform, you see there are now 3 rows. There's the application 1 process, the connection between the 2 processes, and the application 2 process. Here's an example. The total supply by the platform resource is 1,000 units. In this case, the supply has been split between the 2 applications here based on their demands. In this case, there would be a total of 980 available for this application supply, assuming that the other application stayed within its declared unit. And the same thing in reverse. So the sensitivity analysis values apply to each individual element of the report, assuming that the other elements do not change. This diagram from the FASTAR ARINC 653 Get Started example project shows a simple model for a single ARINC 653 module. The model itself follows the guidelines that are given in the ARINC 653 AADL Annex, which is the standard issued by the SAE. So there are standard properties here. A partition is modeled as a virtual processor with certain ARINC 653 properties. The ARINC 653 modules are modeled as processors with certain standard properties as well. And then there are also some properties that the FASTAR tool wants because it handles heterogeneous systems. You need to say that this processor is to be analyzed and scheduled by SPICA techniques, which is the back-end tool that handles ARINC 653. If you take this and instantiate it, the instance folder will appear, and you select the schedule generation tool. Now what this does is produce a folder called derive with a subfolder called AADL. The tool generates the AADL schedule. It's a partition schedule and also priority assignments for the threads in the partition in standard AADL format. That also follows the ARINC 653 AADL Annex. And what this does, of course, is allow you to use the generated schedule with any other ARINC 653 tooling that might come from other tool vendors, for example. I can take this AADL and I can instantiate it. And if I pick this instance, I can run a schedulability analysis, which we'll talk about in more detail later. In the case of ARINC 653, it produces a folder called Visualizations in addition to an analysis report that we'll show later. And this gives a graphic depiction of both the partition windows, which are the wide bars here, and the individual threads within this. If this model were more detailed, it would also show flows of information and deadlines and things like that. Schedulability analysis applies mathematical techniques to determine upper bounds on things like thread response times and end-to-end information flows through systems. This sort of analysis can be used, for example, to assess resource-loaded schedules for CDRs. It takes contention into account when computing these values. Let's go back to the FASTAR Get Started example and further refine that model with enough detail to do a simple schedulability analysis. We've added a thread inside each application process with some of the basic properties needed for a schedulability analysis. The worst case execution time in isolation, the dispatch periodicity, and the priority. We've also added a little information to the processors, the priority ranges. In this case, we've told FASTAR that we want to use a tool called MAST as the backend analyzer because this model is a preemptive priority scheduling model. And MAST supports preemptive and non-preemptive priority in distributed systems. If we take this system model and instantiate it, we can now run the schedulability analysis tool, which is the blue looking glass figure. That will create an analysis folder with a report that in this case is output. The default format is a CSV file. You can actually do your own report formats. There's a report generation tool. And we can look at this to see the results. The schedulability analysis report is divided into major sections for each system operating mode. If you have multiple runtime configurations of the system, it will produce an analysis for each one of those. For each system operating mode, it will list all the resources and some information about those, what the utilization is. For each task, it will also list all the tasks that you have here. The applications and the connections are considered tasks as well. So this is a connection down here. And it will show you information about each individual task, the minimum and maximum latencies. It will tell you what the latencies are relative to, and in the task section that means that they're relative to the release time or dispatch instant of the task, and the jitter. The final section is the flow analysis report. In a model, you can identify an end-to-end flow of information that passes through many connections and threads. For each such flow, it will give you a description of the timing of that flow. It'll list the components that the flow passes through. It will give you incremental latencies up to that point in the flow. It will give you the amount remaining to the end at each point of the flow. And it will also show you what the allowed value is and what the total sum. In this case, the user imposed a requirement of 150 milliseconds, and the analysis said that the worst case flow latency was 140 milliseconds. Now we'll go back to the top level of the model and add two more things. We'll add a sensor that provides information into the applications and whose connections are routed over the network, and a display device. that receives information. And these lines here denote an end-to-end flow of information that goes from sensing through display. Now this is a mixed fidelity model. There is no implementation defined for the sensor. And so what you do is you go in and tell FASTAR that the analysis is black box. The only information it knows about this are properties declared at the interface itself. For example, there is a property declared that says what the message rate is that flows out of it, and there's another property that also gives what the message size is. Similar things apply to the display. The rest of this model has the level of detail that was shown in the schedulability analysis. So for example, it does say that the mass tool should be used to analyze schedulability. And we can instantiate this mixed fidelity model, analyze it, do a schedulability analysis, and look at the report generated for this model. The schedulability analysis report has the same format. There's a section for each system operating mode. There is now a black box resource analysis section, which simply lists that the display and the sensor are black boxes. We don't know anything about how they're implemented inside. No task analysis for the black box. The same resource analyses for the mass tool, and also for the flow analysis we saw earlier. There is also now a flow reported for the end-to-end flow from sensor through the applications to the display. And that lists latencies specified inner to the sensor itself. 100 millisecond is what the user declared. That's the observable timing behavior at the interface. The connection in this case has been allocated to a known resource, and so the message flow over the bus is included in the schedulability analysis report. There are sampling latencies depending on whether the system is synchronous or asynchronous and where those boundaries are, and you can control where the synchronous and asynchronous boundaries are in a system. And again, this is the end-to-end flow, which is 440 milliseconds, of which only 140 milliseconds is between the application processes themselves. We'll briefly walk through a more complicated example model that comes with the tools. It's a multiprocessor system that has switched Ethernet connecting the different processors. I'll briefly just go through the model and point out a few details from the bottom up. So this is the model we have of a dual core processor, which includes cores, memory fabric, and also the controller. And when we do analysis of messages that flow through the system, it will treat the memory bus and the controller as individual resources along the way that might have latencies. If we look at the switched Ethernet itself, the network proper, as it's modeled here, consists of a switch and a series of cables. And each of these are individual resources. Messages queue to get onto the cable on the switch fabric itself may have a latency. If we look at how the cables are modeled, they're done as buses. And we'll see that there are various properties, packet header sizes, and so on. We're going to schedule the network as a non-preemptive priority network. And we've declared properties that say that on this network. It has the preemptive scheduling is set to false, but it is a priority, and we've allowed 8 priority ranges here, which is the Ethernet queue of it, quality of service numbers. One level up from this, we have the overall platform itself. There are 2 dual processor modules, and there are 2 networks, left and right, with crossover connections between them. There are also some virtual buses here. And what these virtual buses do is declare routings through the different networks, and that just simplifies the modeling for all the application developers when it comes time to bind their connections. Instead of giving detailed routings through the networks, all they need to know is here's a predefined route that you can select. And the top level, of course, is the applications that are hosted on this platform. In this model, there are 4 application processes, 2 on the left and 2 on the right processor, with information flows through them. The processors are scheduled using an ARINC 653 discipline. So these are AADL virtual processors that have the properties for ARINC 653 partitions again, and they're down here. If I take this model and instantiate it, then we can take the model and do a schedulability analysis. And in this case, it says it detected 1 error. Now, in a number of the more complicated models that we do, we deliberately put in some examples that do cause errors. This one actually has multiple flows with multiple latencies, and this model demonstrates what happens as you switch between ARINC 653 and preemptive fixed priority scheduling, and what happens when you go from asynchronous to asynchronous systems. So this example model contains all those configurations. We can go down here and look at this analysis report. The schedulability analysis report for the network system again has a section for each system operating mode. There is a section that lists all the masked resources, and you can see this is each individual resource. The masked analysis applies to the parts of the system that handle message communication, the networking, and so on. But that includes the controller, the memory bus, things like that. If we go down, we'll find the masked task analysis. And again, the tasks are connections. Each message flow over each individual resource is an individual task. Here's a message that flows over the controller, memory bus, individual cables, and each of those has their own analysis result. Further down, we have a section for the parts of the model that are analyzed by SPICA. In this case, that's the ARINC 653 processors. Here's a list of all the resources, both the partitions, which are virtual machines, and their utilizations, and the hardware processors themselves. Here's a section that lists the individual tasks. This model has 3 flows. They're all identical. I mentioned before we have examples that deliberately introduce errors. It's the same flow with increasingly tighter bounds, and the tightest bound is the one that generated an error. And if we look through here, we'll see that the flow consists of a thread execution followed by the sequence of message transmissions over the individual resources as the message flows through the network. There's a sampling latency, and the compute time, the final latency, is the time it takes for the thread to get the message and complete executing. And that's a quick walkthrough of the FASTAR tools. All of these tools are available on the CAMA library of tools and other assets available from the Avinium CAMA website.